Okay, so today we're going to be doing something a little bit different in Math 20, and I think different is a good thing in this case because I don't know, again, what you thought of the last couple concepts we've done, but today we're talking about sine law. So today's lesson is going to seem a lot more like what trigonometry felt like back in Math 10C, and I do think you guys will like this one a little bit more. It's a little bit more real world based, if that makes sense. Anyway, so here's today's plan. First things first, before we get to that new thing today, I want to review trig ratios on the Cartesian plane. We've spent the last couple of days working on this. I know it's like not really the most focused thing. It's kind of just like, oh, here's a kind of question you can do like this, and here's a kind of question you can do like this. Let's see if we can try to like simplify that today and just make sure that we've got a solid understanding of it. Anyway, then we're going to move on to something much different, solving for missing angles and sides in non-right triangles. So the key here, again, non-right. All the triangles we've been able to solve both in this course and in Math 10C have been right triangles where you got a right angle. Now we're going to talk about how to solve like other triangles. That was a terrible triangle I just drew there, but whatever, you get the idea. Anyway, once we finish that, of course, as always, practice time. The goal for today will be to know how to find sides and angles in triangles that don't contain right angles, right? There is a new thing we'll introduce today. You will need a formula sheet at one point, so make sure you got that out and handy. Anyway, let's get rolling. So again, first things first, let's do a little bit of review of the stuff we've done the last couple of days. I want this to be like focused for you guys. So I want you to see whether you get this or not. And you can work in partners if you wish. Find the exact values for each of the three primary trig ratios for the terminal arm passing through the point 2, -5. Pause the video here. Give this one a try. All right, I'm going to go over this one now. So 2, -5. First things first, let's actually plot where that point is. So 2, -5, that looks like it's down here. Connect it with a terminal arm. Do my best on here. I don't really have a ruler, of course. And then as always, when we got a point and a terminal arm going through it, since we're looking for exact values of trig ratios, that kind of implies we need to have a right triangle. So let's make a right triangle using our X and our Y. So in other words, there is our right angle. The X direction is going to be +2, and the Y direction, it's going to be -5. Now, you could have said +5 there, but it's just going to end up giving you trouble. You'd have to end up using the cast rule to fix that. I would recommend like using the actual coordinate, 2, -5. Now, just again, with the three primary trig ratios, remember it's SO, CA, TOA. That's how we can remember sine, cos, and tan. And you'll notice, at least for sine and cosine, you need to have the hypotenuse length in order to be able to do anything with those. In this triangle, obviously, we don't have the hypotenuse length. So I think first things first, we should use Pythagoras, a² + b² = c², to find that hypotenuse length. Anyway, let's get that done real quick. So 2 squared plus in brackets, -5 squared. Always remember when you have a negative, put it in brackets so you actually square the negative. Equals, we'll call this R, like stands for radius, but whatever you can call it C if you want to, it doesn't matter. So equals R squared. 2 squared is 4 plus -5 squared is +25. That equals R squared. 4 plus 25 is 29 equals R squared. And then remember, this is the nice thing about that term exact value. Part of what that means is like if you square root a number, you just leave it as a square root. Really, an exact value just means you don't round your decimals or anything. So try to like write it without having that, like as a fraction or whatever you need. So in this case, when you square root 29, it's going to be 5 point something, right? It's a disgusting number. So instead, let's just say R equals the square root of 29, because that's exact. That's an exact value for what R is. I'll even label that on there, square root 29. Awesome. All right, so we're ready to go here. Once you got that, like I've said before, that's really like the longest part. We just need those exact values for sine, cos, and tan. So let's start with sine. Keep in mind, this is your angle here. So we'll say sine of theta equals your opposite side. Opposite of theta is -5, so -5 over hypotenuse, which we just found was square root 29. That's it. That's all you got to do there, right? It's not asking for the value of the angle, which you could find by using inverse trig on this, and then you realize you'd have a reference angle because you never use inverse trig on a negative number and blah, blah, blah. All it's asking for is the exact value of the trig ratio, not the value of the angle itself. So that's good for that one. Now let's do the other two, cosine theta. Cosine theta is adjacent over hypotenuse. Adjacent is 2. Hypotenuse is square root 29. That one is all done. And then the last one, of course, tan theta. Tan, as you can see in SOHCAHTOA, is opposite over adjacent. So opposite is -5 and adjacent is +2. And I guess you could simplify that, like -5 divided by 2 is just -2.5. I'd leave it as a fraction. It really doesn't make much of a difference either way. And those would be your three answers. One thing just to kind of drive this point home a little further, remember the cast rule, C-A-S-T. The cast rule tells you whether sine, cosine, or tangent are positive or negative in any given quadrant. We're down here in quadrant 4, which is the C quadrant. Since it's the C quadrant, what that means is the only thing down there that should be positive is cosine. And as you can see from these three trig ratios we came up with, yeah, the only thing that was positive was cosine. So that's a little bit of extra reassurance just to tell us that we did it right. If this question was asking for the value of theta, you could pick any one of these three and use inverse trig on it, just as long as you made it a positive, and then realize that you're in quadrant 4, so you'd have to just come down from 360 degrees. What I'm trying to say here is, though, making 3 trig ratios for something, it's usually pretty redundant. So unless a question asks, write the exact values for each of the 3 trig ratios, you don't usually have to do it. Anyway, that's enough rambling for me. Let's go on to the next question. Find the exact value of each of the primary trig ratios, so kind of like the last one here, for an angle, excuse me, for an angle of 210 degrees. I didn't give you a point it's passing through here, so I'm going to give you a huge hint. Reference angles and special triangles. That's my huge hint. Pause the video here, give it a try. Okay, so first things first, as always, you should try drawing what this is, right? So here's our Cartesian grid. 210 degrees, well, I know this is 180 and this is 270, so 210 must be about right here. Now, it didn't tell us a point that it passed through. It wasn't like the last question, so we couldn't use Pythagoras on there, but we do know we have 210 degrees, and that's going to form a right triangle with our x-axis right here using a reference angle. And since we knew this is 210 degrees, that reference angle coming down from 180 down to 210, that reference angle must be 30 degrees. 30 degrees is one of those special triangle angles, right? So ding, 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 a little bell should go off in your head. We know this is a special triangle. Now, if you look at your special triangles on your formula sheet, I'm pretty certain what you're going to find is that opposite of 30 degrees, I can't obviously pull one up on the screen here, but opposite of 30 degrees is going to be a side length of 1. Adjacent to this is going to be a side length of square root 3. And the hypotenuse of this, because the hypotenuse is coming off across from that right angle there, the hypotenuse, I believe, is going to be 2, right? Now we have all 3 sides. It's just like that last question at this point. Just we weren't given a point that it passed through. So we have to use a special triangle to extrapolate from that. Keep in mind, this line, like this terminal arm, can keep going and going and going forever. So it goes through an infinite number of points. The whole purpose of special triangles is it shows the relationship, just like relative speaking, to each of these side lengths. So we know, for instance, relatively speaking, for every 1 in the y direction here, we have 2 in our terminal arm direction for our hypotenuse. So in other words, if this line kept going and going and going forever, whatever our y value is here, the hypotenuse is going to be double it. Now, before I do anything else, just because I'm used to doing this and I've seen how it goes before, think about how these 3 numbers play into coordinates. This top number here, this square root 3, that's technically your x coordinate. Notice x in terms of a Cartesian plane here, x is going to be negative. So just because I'm catching on to this early, I know that that's going to be negative square root 3. Likewise, notice our y value here of 1 coming down below the x-axis. That tells me it's going to be negative 1. The hypotenuse here of 2 is still going to be positive 2. That's the thing about these terminal arms. The length of the terminal arm is always a positive number. It's just because it doesn't really have a Cartesian grid coordinate to it. So it still all counts. Now, if you didn't notice that those were negative, that's okay. You would have had to catch it in the cast rule when you actually put things together. So now we're ready to go. Let's get our primary trig ratios going. So we have sine of, we actually know the angle here, so I won't say sine theta. It's sine of 210 degrees equals the opposite side. So opposite of your reference angle, which is just serving as like a blueprint. Opposite of that is -1 over hypotenuse, which is 2. -1 over 2. Notice the cast rule, C-A-S-T. Only tan should be positive down here. Sine being negative is no concern to me at all. If you didn't label those negatives, you would have caught it in the cast rule and you would have just had to force it to be negative. You can always test this in your calculator. Type in your calculator sine 210. It should give you -1/2. So I know I got that one right. That is a relief. Anyway, let's get those other 2 ones done. So cosine 210, Remember from SOHCAHTOA, cosine is adjacent over hypotenuse. The adjacent side here is negative root 3. So negative root 3 over 2. And again, you could double check this. If you put cos 210 in your calculator, I'll just do it right now. You get like negative 0.866 and then a bunch of other stuff. If you try negative root 3 over 2, you'll get the exact same thing. Last one up, tan 210. Remember, tan from SOHCAHTOA is opposite over adjacent. Opposite here is negative 1. Adjacent is negative square root 3. You could leave it as that. I wouldn't recommend it because it's a negative over a negative. So why don't we clean that up? When you have a negative on the top and a negative on the bottom, it just becomes positive 1 over positive root 3. So I would say that right there, probably a much better answer. Anyway, cast rule can save your life here, right? As long as you use your reference angle and then the cast rule, you can figure out whether it's positive or negative. Another thing that saves your life here is just checking your answers. It only takes about 2 seconds, and it just confirms whether you got it right or got it wrong, right? The trickiest thing in this question, in my opinion, was identifying that that was a special triangle to begin with, because 210 does not sound like a special triangle, but when you get a reference angle out of it, you're golden, right? All right, one more review question. Solve for theta, where theta is between 0 and 360. That's just kind of standard, right? For sine theta equals negative square root 3 over 2. Give you a hint here, inverse trig and cast rule. Those are my hints, inverse trig and cast rule. Pause video here, give this one a try. Okay, I'm gonna go over this one now. So like I said right before I paused the video for you, the hint here is, inverse trig and cast rule. So first things first, when you use inverse trig on a number, never do it on a negative number. So even though it's negative square root 3 over 2, don't use inverse sine on that, right? So instead, I'm going to go inverse sine of positive square root 3 over 2. The whole purpose of that is it's going to spit out a reference angle for me. And the reference angle can be used in any of the 4 quadrants to figure out what's going on. So if I use inverse sine of square root 3 divided by 2, just a note, when I put that in my calculator, when I do square root, it puts brackets around it immediately. Make sure you close those brackets. You're doing just the square root of 3 divided by the square root of 2. So on my calculator, I know this might seem silly to some of you, but it is important. In my calculator, it looks like this: square root 3, and then end that bracket, and then go divided by 2, right? Inside the sine negative 1, of course, right? Inverse sine. Anyway, inverse sine of that gave me 60 degrees. If you were really keen, you would have saw that was a special triangle, right? 60 degrees exactly. That's kind of cool, right? And that's going to be our reference angle. Now, the whole purpose of a reference angle is it serves like kind of as a blueprint as to where you're going to be. Your cast rule will tell you the rest of the story. Cast rule is going to tell us, since sine is negative here. Since sine is negative, we're definitely not in the all quadrant, and we're definitely not in the sine quadrant. That means we're down here or we're down here. You have to assume you're in both. So let's start with quadrant 3, the T quadrant, right? So quadrant 3, since this is 180 degrees and we have a reference angle, which always comes off the x-axis, of 60 degrees, we just need to go 180 plus another 60 degrees. Because in quadrant 3, we know our answer is going to be somewhere between 180 and 270. So 180 plus 60, that's going to give us 240 degrees. There's one of our answers. In quadrant 4, similar idea in the C quadrant over here. Just notice we're coming down from our x-axis. Our x-axis is 360 degrees. We're coming down by our reference angle is 60, so it's going to be 360 minus 60, which of course is just 300 degrees. As much as I sound like a broken record here, you can still test these answers. If you type in your calculator sine 240, it should give you the exact same thing as whatever this is. It'll be a negative number for sure, I guarantee it. Same with sine 300. It'll give you the exact same thing as this negative square root 3 over 2. I promise, right? Anyway, that's always a good way of checking your work. We're going to move on to actually our new information today. We're already like 14 minutes into this video. Oops. But this hopefully will be a nicer concept. Hopefully this won't be as crazy and confusing. It's solving non-right triangles. So here we go. Clearly on the screen right now, you can see we have a non-right triangle, a triangle that does not have a right angle in it. In Math 10C, you may have actually solved non-right triangles. This might have been a question you were given at some point, by making a non-right triangle into 2 right triangles. That's always a nice way of solving it. It just takes a little bit of time. That's basically where you say, look for your peak. So right up here, bring it straight down, and then bingo, bango, bongo, we got 2 right angles there, right? So we have like a right triangle in the corner here and a right triangle over here. In Math 10C, what you probably would have done is you would have said, okay, well, since we have two right triangles, we can use SOHCAHTOA on these. You could also use Pythagoras on each of these two triangles that have now formed. You could have found this side, we can call it H for height. That's the opposite side here, and that's a hypotenuse. So you could use like sine of 35 equals H over 22, solve for H, and then you have this, and you go, oh, okay, that's our opposite side in this one, and you're looking for the hypotenuse. Oh, dang, opposite hypotenuse, that's sine again. You could say sine 54 equals opposite, which whatever H was, which you found over here, and then put it over X. Oh my goodness, a lot of work, right? So you're probably shaking your head right now going like, slow down, slow down. That is a lot of work, right? Too much work. There must be a better way. There always is a better way. Infomercials have told us there's always a better way. Well, there is. It's something called the Sine Law. This is used to solve for missing side measures and angle measures in non-right triangles. And believe me, you're going to be so thankful that this thing exists because it saves so much time and so much effort. Here's what I got to do. Before we introduce how to use sine law and all this and when it's used, I want to just remind you of something. We haven't talked about it at this point in this year, but when you're in triangles, when you're dealing with like unknowns or knowns or whatever, capital letters, so the uppercase letters, will always represent angles. Lowercase letters in a triangle will represent side lengths. Same letters, this is really important, same letters, so a capital A and a lowercase a, these are opposite to each other. So if I go back to this guy, I'm going to erase all my stuff that I put on here. If I go back to this guy, we could have set this up to say that, okay, we know this side over here, it's a lowercase x, right? So lowercase x is the side length because lowercase letters are side lengths. That means this angle down here, even though we know it, we could have called that capital X, right? Maybe this side over here of 22 feet, that'd be a lowercase y. That means this angle over here is a capital Y, okay? This is just a convention to help us keep things straight. Believe me, you'll be thankful for this. As you might imagine, if we're gonna use our last letter here, we'll say lowercase z is this long side length down here, and that means this angle up here would be capital Z, right? The whole idea here is we have a system that allows us to identify and match opposite pairs of angles and side lengths. And that will be important for the sine law. Anyway, back to this. So sine law, or the law of sines, as this picture says here. There's two versions of it, and you use each one depending on what you're looking for. There's one version that says sine capital A, obviously capital letters are angles, they have to go inside of sine. Sine capital A over lowercase a equals sine capital B over lowercase b equals sine capital C over lowercase c. What this means is sine of any angle, A, B, or C in your triangle, divided by the side length across from that angle is equal to sine of any other angle, B or C, in that same triangle divided by the side length opposite of it. The reverse is true as well. You can flip sine law upside down and put sides on the top. It works as well. The whole purpose of this is if you are looking to find a missing angle, use the version of sine law that has sine on the top. If you're looking to find side lengths, use the version of sine law that has the side lengths on the top. Now, there are two cases in which sine law will work. And I don't really stress memorizing these cases because it'll be pretty clear once we see some examples. I'll show you there's a really quick trick that allows you to identify when you use these. The first kind of triangle, though, is the SSA triangles. This means you have two sides and a non-enclosed angle. In other words, the angle that's not in between those two sides are known. So you need to know three things. You need to know two sides and the angle that was not in between them. The other possible case is you know two angles, so ASA, two angles, and one side length. It doesn't have to be the side length in between those angles. It can be any other one. So they just listed it like that. It's whatever. But if you know two angles and one side length, you're golden, right? Anyway, I don't like those two rules too much. I introduced this and this because the next kind of sine law, it's called cosine law. Huge surprise, we'll deal with that in a couple of days. Those ones are a little more important to memorize. But let me show you how you really can use this here. Oh, sorry, here's some pictures of this. So case one, you know, two sides and a non-enclosed angle. So it's a side, angle, triangle, right? So you know the two sides and not the angle in between them. The other case is, you know, one side and two angles. It doesn't have to be any specific two angles. You're golden. Matter of fact, this case two is kind of silly because guess what? If you know two angles, you like low key actually know the third one. Remember, inside of a triangle, all of your angles, all three angles always add up to 180 degrees. So if you know two angles, you actually do know the third one. You just have to do a really quick little bit of math. That's all, right? Anyway, moving on. So this is what I was alluding to. Why I say you don't have to remember it's like SSA and ASA triangles. Ultimately, here's the key behind sine law. Ultimately, the entire idea is to see if you can get an opposite pair. What I mean by that is an opposite known pair. If you know two things that are opposite to each other, so one side length and the angle across from it, you're golden. You can use sine law. That's all you got to look for. This serves as what I will call a key that you can use to form other sine law relations. Remember, sine law just said sine capital A over lowercase a equals sine capital B over lowercase b, which equals sine capital C over lowercase c. You can like cut out the middleman here, just say it's this equals this, or you can say it was like this one and equals this one. So you can cross out this guy. It's whatever, right? These are all equal to each other. They just serve as a key. So with this triangle that I got here in the corner, I don't think we're actually solving for it. I think I just threw this in as kind of an example. Maybe we do solve it in another question here. Maybe I'll eat my words. Anyway, sorry. What we need to look for is, do we know an opposite pair, an opposite known pair of things that are in this? If you look at this triangle, you can see we don't know this angle, or sorry, this side length A. We do know its angle across from it, but that is not an opposite pair because we don't know them both. Notice we know the side length 12 over here, but we don't know the angle across from it, so that won't be our opposite pair. But here's the key. We know this angle, 34 degrees, that was known, and we know the side length across from it, right? Directly across from it. That right there, the 34 degrees and this 18 meters, that would be useful as a key. So in this triangle, we can use sine law. If I go back to that picture here, notice we can use sine law. Let me just erase all my little scribbles here. We can use sine law in this first one, not only because it's an SSA triangle, but also because we know this opposite pair. We know 115 degrees and 49. So sine law will work. In this one, we know 29 degrees and the side length across from it. There you go. That's our opposite pair. We can use sine law in that one. Let's actually use sine law now. Let's stop rambling here and actually use it in a question. Oh, sorry. Oh, wow. Look at that. Can we use sine law on this to find angle X? Okay, so here's an example. Think about whether or not we can get an opposite pair going here. We're looking for angle X. We know the side length across from it, but that doesn't help us because we don't know angle X. Shoot. We know this angle of 115 degrees, but we don't know the side length across from it. So we don't have an opposite pair, and then we don't have an opposite pair this way. So notice, since we cannot form an opposite pair, we cannot use sine law on this one. This is a question that you would not be able to solve using sine law. So we won't worry about triangles that are unsolvable, at least not at the moment. Let's finally get to an example here. This has kind of been beating it to death. So find the measure of angles X, notice capital X because it's an angle, and capital Y. Let's do this one together. Remember, the key to sine law is to see if you have an opposite pair. Have a look at this triangle right now and see if you can identify an opposite pair just by scanning it. Hopefully what you notice is we know this angle of 80 degrees and we know the side length directly across from it, which is 82. That will serve as our key. It's our opposite pair, which is known. So we can use that. Now, the other thing I want to mention is notice we're looking for angles. There's two different versions of sine law. There's the one with sine on the top. That's used to find angles. And there's one that has the side lengths, the lowercase letters on the top. Those are used to find the side lengths, right? Since we're looking for angles, let's use the one with sine of an angle on the top. So here's what I'll do. I'll start with my key. We're going to use the one with sine on the top. So let's start with our key. So it's going to be sine 80 divided by the side across from it. So 82, sine 80 divided by 82. And this will equal sine of another angle. Let's focus on finding X. So sine X over the side across from X, which is 75 kilometers. We want to solve for X. It's going to take a little bit of algebra, a little bit of rearranging an equation to get that to work. If we want to get X all by itself, I think the first thing we need to do is multiply by 75 on both sides. That'll get rid of this divide by 75. So if we multiply by 75, that's gone. We got to do it to this other side though. Throw this in your calculator. This is going to get a little messy, but I'll have a little hint for you here in a second. So 75 times sine 80, close the bracket around that 80 so nothing else gets trapped in it, and then divide by 82. Here's what happens. Every single time you're going to do this, you're going to get a really disgusting number. That's just the nature of trigonometry here. We're not dealing with exact values with sine law because ultimately we do need to round. But 75 times sine 80 over 82 in my calculator gives me 0.9007 and then a bunch of other decimals. I'm going to be honest with you. In trigonometry, you can round to 4 decimal places, and you're pretty much always guaranteed to be about as exact as you need to be. If you're not comfortable with that rule, you can round to more. I would not round to only 2 or 3 decimal places. That's going to screw up your answer. But rounding to 4 decimal places is just a nice middle ground. I always do that when I do this. So anyway, 0.9007, that is 75 times sine 80 over 82, and that's equal to sine x. Now here's the question. We want to get x all by itself. Well, how do we get rid of a sine? Hopefully you're remembering inverse sine. We got to take inverse sine of both sides here. So inverse sine and inverse sine. That's obviously going to knock out our sine here. So take inverse sine of that answer. It's even better if you like put the whole thing in your calculator, but if you just put 9007 in, you should get, let's just round to the nearest tenth as a final answer here. You should get somewhere in the neighborhood of x, well, maybe I should save some space here. X equals about 64.3 degrees. I didn't say what to round to, so rounding to the nearest tenth as a final answer is a pretty good idea. But when you're rounding, when you're doing your whole sine calculations, rounding it to 4 decimal places is pretty safe. Anyway, that's just our x. We now need to find our y. We're kind of in a bit of a pickle here by the looks of it, because we don't know our opposite side length. I'm actually wondering here, I don't know if we can even answer this one with what we've got. Oh, no, we can. Sorry, my mind completely blanked. Look at me go. See, even I'm screwing up here. We know 2 of our angles in this triangle now. 80 degrees and 64.3 degrees. We know 2 of our angles in a triangle. If you know 2 angles in a triangle, how do you find the third one? Hopefully you remember, it is the 180-degree rule. I was tempted to use sine law again, but I was gonna be like, oh, I'm hooped. We don't know what this side length is over here. I can't use sine law again. And I would have been right on that. Fortunately, the 180-degree rule still comes into play. So to find y, maybe I should do that better. Capital Y like this, there we go. Capital Y is gonna equal 180 minus the other angles. So minus 80 and then minus 64.3. And that is going to give me a second here, 180 minus 80 minus 64.3. Oops, somehow I pressed plus on my calculator. Look at me go. Okay, so that's going to be y equals 35.7 degrees. There you are. 180-degree rule comes in, saves our lives every single time. You don't have to use sine law a million times. Matter of fact, usually in a question, you don't usually have to use sine law more than once or twice. Anyway, here's another example. Find the measure of sides A and B. So this time we're looking for sides rather than angles. Looking for sides is actually easier in my opinion. Let me show you this one as well. Follow along. So we're looking for side A and B. Let's start by focusing on finding side A just because alphabetical order and all that. Looking at this triangle though, we need to start by making an opposite pair. We need that key. If we look at this triangle, 37 degrees, we don't have the side length across from it. 23 degrees, we don't have the side length across from it. And 50 meters, we don't have the angle across from it. But remember, even from that last question, if you have 2 angles, you actually like low-key have the third angle as well, right? So to find this angle here, I'll just call it like question mark. To find question mark is going to equal 180 minus the other 2 angles. So minus 37 and minus 23. So 180 minus 37 minus 23. That gives us a nice round. Question mark equals 120 degrees. So I'll just fix that. 120 degrees is our angle up there. So now that we know 120 degrees, notice this, we have our opposite pair. That's going to serve as our key. So we can set that up first. Notice we're looking in this question for side lengths. Let's use the version of sine law that has the side lengths on the top. So I'm going to start by putting a side length on the top, 50 meters, over sine 120 degrees. That's our key, right? So the side length divided by sine of the angle across from it equals the side length we're looking for. We're going to look for A first. So A over sine of the angle across from it. Well, the angle across from A is 23 degrees. So sine 23. We want to get A all by itself. So let's multiply sine 23 to the other side. So we're going to multiply that over. Sine 23 is going to multiply by this. So sine 23 times 50 divided by sine 120. Throw that in your calculator all in one go. So sine 23 and the bracket times 50. Get an answer and then divide that by sine 120. And I'll just round to the nearest tenth because why not? A is going to equal to the nearest tenth 22.6. 22.6, and I guess that's meters. So we should include a unit there. Nice. 22.6 meters. All right, so that's A done. Now we need to find B. Here's the good news. Finding B, it's going to work almost the exact same way as A. Use your key again. We know our key is 120 degrees and 50. We're solving for a side length, so let's put 50 on the top. So 50 over sine of the angle across from it is 120 equals B. That's what we're looking for. Divided by sine of the angle across from it. The angle across from B is 37. All right, so now we're looking for B. So let's multiply by sine 37 on both sides. For multiplying by sine 37, there you go. That was a little iffy. Throw that in your calculator though. Sine 37 times 50. And I usually just get an answer just so I can move on and then divide that answer by sine 120. This is going to give us B equals, once again to the nearest tenth, just for consistency here, B equals 34.7 meters. And I mean, visually, I can see that B is a longer side, so it makes sense that it's a longer answer. It's not as long as that 50 meters on the bottom. Everything seems pretty fair. I think we've got a pretty good answer on that one. So bottom line, when you're using sine law, just come up with your key first, right? Look for an opposite pair. Sometimes in a question like this, it's sneaky and you have to find something first. But if I'm asking you a question, it's solvable. So don't you worry. All right, I think this is the last one. It's a word problem. Romy is standing 30 feet from the base of a slanted tree. She measures the angle of elevation from her ground position to the top of the tree to be 65 degrees. So between the ground and her line of sight to the top of the tree, it's an angle of 65 degrees. The tree is growing at an angle of 75 degrees with the ground slanted towards Romy. Calculate the slanted height of the tree. This picture in here, I think I just threw it in because it was kind of goofy, but that's not an accurate depiction of what these people are looking like here. So calculate the slanted height of the tree. I think the easiest way of going about this first, let's draw a picture. Let's try to figure out what on earth is going on. So we know Romy is standing 30 feet from the base of a slanted tree and the tree is slanted towards her. So why don't we draw the ground first? We're going to draw the ground here. We'll say Romy is standing right here and we'll say the tree is right here. Now that distance, as the question says, is 30 feet. So I'll label that first. 30 feet between Romy, maybe I'll even just put a capital R, and the tree. I'll just put a capital T. Wait a minute. Yeah, you know what? Capital. Yeah, because it'll be an angle there. So we'll use a capital. Anyway, so Romy's here and the tree is there. Now the angle of elevation from her ground position, so from the ground to her line of sight, is 65 degrees, and that takes it to the top of the tree. And the tree is growing at an angle of 75 degrees with the ground slanted towards Romy. So maybe, you know what? I think I'll draw the tree first. 75 degrees is a pretty steep angle. It's like this, more or less. And then we'll draw, so then we'll label that 75 degrees. And then we'll draw the line of sight from Romy to the top of the tree. You can do like a little arrow, so it's like the top of a tree. Romy to the top of the tree is that. There we go. And that is 65 degrees. There we go. Hopefully that's legible. It's a little sloppy. Anything else in this question? Let's just scan it again. So we got 30 feet between Romy and the tree. 65 degrees is her line of sight. 75 degrees is the way the tree's growing. We're looking for the slanted height of the tree. So in other words, actually how long that tree is. So this will be, I'll just call that our lowercase x. That's what we're looking for here. So now that we have a picture drawn, which honestly I think is like the most work in this whole thing, in my opinion, that is, some people would disagree. Let's see if we can actually solve this. Clearly, it's not a right triangle. We don't have a 90-degree angle here. And obviously, we should be using sine law because that's what this lesson's all about. Do we have an opposite pair? It looks like we actually do, but it's kind of like that last one. We'll have to solve for whatever this angle up here is, right? Notice we know 65 degrees here and 75 degrees here. This angle up here, I'll just call it question mark. That angle up there is going to be found from the 180-degree rule. So we're going to go question mark equals 180 minus 65 minus 75. And I'll throw that in my calculator quick. 180 minus 65 minus 75. That gives us a nice 40 degrees. So I'll erase the question mark in this now. We got 40 degrees. So now that we know that's 40 degrees, we have an opposite pair. So in other words, we can solve using sine law. If we're looking for the slanted height of the tree, that implies we're looking for a missing side length. Since we're looking for a missing side length, let's use the formula for sine law where the side lengths are on the top. So let's start with our key, put the side length on the top. We'll say 30 feet over sine of the angle across from 30 feet, which is 40 degrees, equals the side length we're looking for, that's x, divided by sine of the angle across from x. The angle across from x would be that 65 degrees. We want to solve for x, so let's time by sine 65 on both sides. I won't write it out, but I'll just go sine 65 in my calculator, multiply that by 30, and then divide that answer by sine 40. And we get, and we'll just do it to the nearest tenth, x equals to the nearest tenth 42.3 feet, just to put our units in there. And there you are. That's a word problem with that, right? Realistically, think about what that means. What that means is if you have something, some really tall object slanted towards you, if you can just measure the angle it's slanted at, the angle between the ground and your line of sight to the top of it, and the distance between you and the object, without actually literally measuring the object, you can calculate it, right? So when you see something really, really large and someone's like, yeah, I know how big that is, they calculated, like the height of Mount Everest, for instance. They just use trigonometry to find that. It's not like someone actually took like a measuring tape and went up and measured it, right? That would be a lot of work. If you have some accurate measurement tools for angles and stuff, you're golden. That's the whole field of surveying. Anyway, I'm going to stop rambling. That was already a very long lesson. I apologize. I thought it was going to go a lot quicker than that, but I was wrong. For practice, you can work on your homework booklet. You can now complete up to question number 6. You could do up to question 5 yesterday, so there's only one sine law question I'm going to get you to do right yet. If you want some extra additional sine law questions, though, page 108, questions 1 to 5 would be a good starting point. We're going to build sine law even more in the coming days. Anyway, if you need any help, reach out to me. Best of luck.